Once that starts, I'm going to start talking. I'll go ahead and make this big. Well, maybe I'll just do it the way I usually do it. I haven't set my computer up to make that convenient today. So I'll just do it the way I sometimes do it, making it big like this. There we go. All right, so the idea for this today is to show some tools for Python for applied scientists, right? And this could be other interesting people. And I'm glad Ben is here today because I do specifically mean by other interesting people, my own colleagues and people who may be interested in teaching this kind of stuff. Some of you have seen me show this slide before. I have encountered resistance to learning numeracy and math tools. I know you guys have self-selected to be here, but some of the context for this Python bootcamp is relevant for what I'd like to say on this slide, is that often in any room of people, including scientists that are, publishing successful researchers, there'll be some people that are intimidated by math and statistics and computer programming, forget it. I have encountered this amongst the taught research students here at Harper. This is almost a direct quote of what a young person said to me one time in a stats class, and I was shocked when this person said it like they said it in the middle of a class full of people, but that's always there. It's been there my whole career, and a way I've tried to help people get on board and appease those fears is to try to creatively try all sorts of ways to lower the barriers and lower that anxiety and be inclusive of materials that I create and to curate high quality results and to constantly give as much as I can. But that always isn't enough all the time. There are some people who are set and determined not to learn stuff. I know, again, like I said, I know that it's a self-selecting group here, but I feel sometimes that I'm under pressure to justify why this stuff is important. It's important for all students of science to have the tools in their toolbox to understand evidence, okay? But for the other interesting people, it's also important for continuing professional development. Even if you don't use those skills every day in your job, the ability to make your own decision about evidence created by those tools is essential. And let's say that you don't consider yourself a scientist. Some students don't, and some of you very possibly will go on to have jobs where you don't create information from data every day. But I would argue that to be an effective citizen that participates fully in our society, you must be able to make your own decision based on real evidence. And understanding evidence based on climate change, how vaccines work, what the GP tells you about your own health, nutrition decisions, all of that stuff will be heightened and enhanced if you have the ability to make your own decision about evidence. Employability is another one. I have said it in various forms before, but computational and numerical skills will never make you less employable, and they're transferable skills as opposed to point and click programs like SPSS and GenStat, which aren't transferable skills. We know that reproducible data converted into information in form of scientific evidence and other kinds of evidence is best practice, and all professions have a literature on this, whether it's people educating vets or animal science folks or other people. Ecologists are very much like this as well. The professions themselves have guidelines that recommend reproducible data like you do with computer programs like Python and R. And finally, we have this thing in education that I'm old enough. I cast my eyes across. No matter what any of you think, I'm definitely the oldest of you in here by far for most of you. Um, and when I was in school, even though I didn't study computing, we all took education formally as a core component on how computers work. And today we don't do that, but we've created a situation where in sciences, especially, we have computing haves and have nots. Of course, by the have part and have not part, I mean you have knowledge or you are knowledgeless about how computers work. So it's another justification. I really resent um, some of the resistance I've had from my own colleagues at times. It's rare, but I have encountered it where maybe because of inherent limitations in our training that has led a person to their current station, that they choose. They say, well, our students don't need to understand computers or math because they'll never ever use it in their career. But I think it is one of the most astonishingly arrogant things or arguments I've ever heard for not doing what the rest of the world, the scientific world anyway, recognizes best practice. Okay, and then finally, in my Twitter timeline, I see this kind of modern quip quite frequently these days. AI will not replace you, but people using AI will. But you can replace that with programming data-driven decisions, evidence-driven decisions. Um, we're turning into a data-driven society. And so it harkens back to the thing I said about employability. And then not only that, there's literature for this. So both, I'm not going to belabor this very much, but there's a literature for it in education for statisticians who teach non-cognitive, non-cognate students, as they're referred to, who are non-statisticians. But also in every field of the applied sciences, there is there is a formal research literature on best practices, which these days means programmatic creation of evidence, reproducible creation of evidence. Okay, so all of these really are reasons why we should learn how computers work and how to give them instructions in the form of scripting to convert data into evidence. I had some reflections on the RStats bootcamp that we've gone through in here. The intention, as most of you know, uh, is to be a completely open resource, an altruistic resource. It's not a course that we offer. It's not something that is part of my job to have created. It's something that I wanted to create to include people and give them an open resource that I thought was high quality and well curated. But also just to help folks who want to start using R to be helpful. It needed to be self-guided. That was an important part of the design principle that I use so that folks could access it themselves and they could work at their own pace. You know, we're all very busy. Sometimes we do this on the evenings and weekends or over our sandwich if we're eating al desco someday. So it was important for me to design a self-guided resource. Now I chose as part of the design to do this in tutorial style. And the intention of that material, if you've looked at it or worked through it, is to read some words that I've carefully written as briefly as I could, to run the code, to experience running code in the R environment, and then to work on some problems. All of this takes time, this tutorial style that I chose. Okay, and that was a design choice. It's not the only style, though. Um, I wanted to reflect on what worked. There has been incredibly good uptake by many students. If if I were asked by someone how well the boot camp works, I'd probably cite the fact that there have been over At this point, believe it or not, over 15,000 questions asked in threads in Slack associated with our stats in the boot camp. Are they all about the boot camp? No, there's probably a few thousand just restricted to the boot camp. Of course, I've been running it about 3 or 4 years now in various forms. Another thing that has really worked is it's been nice to have what I call a standing resource. It's easy to maintain. I can improve it. I can add to it. I can add examples as I think of them or as people request them. It's very convenient that way. I've also think something that's worked is a number of colleagues and students have used it to teach or to increase their skills with what I refer to as, tame material. What do I mean by tame material? I mean, it's material I've tuned towards the audience here, and it's material that myself and people in our community and the Herrig group and some others who have used it, even some people who use my material who are my friends at other places, are able to support. It's easy for us to support because we know the tame material. That's worked really well. Thing that has not worked is that, well, some students just don't engage with it's extra work. You can elect to or not to engage. You don't get any marks for it. And so probably the students who need to engage most, who could benefit the most anyway. I say need, but the students who could benefit the most, I'm talking about taught courses now. They tend not to engage. They need it the most, but they're the least likely to engage. Those two things are they're probably related. Another thing is that the tutorial format that I chose. Now there's a handling time. This is an ecological term. It refers to a predator. Let's say it's a fox catching a vole. Now, to catch the vole and eat it, the fox has to track the vole, find the vole in the first place, track it down. Maybe it's under snow, has to listen and be quiet, not make any noise. Finally, it needs to attempt to catch it. Maybe it misses it the first time and has to wait another hour. Finally, it can catch the vole and gulp it down. Okay, all of that time from start to finish is referred to as the handling time. In tutorials, the handling time for knowledge capture, you're a knowledge predator, is fairly high for tutorials. I intend people to read the stuff, think about it, run the code, type the code if they can. I encourage people to type the code from scratch. That is a challenge because not everybody has time. Sometimes people want to dip in and have a good reference, and they don't have time to read a whole, web page that I've designed to last an hour or two of your time. So that's a challenge. I've thought of some solutions, but another one is having this kind of whole set of material, a whole boot camp that's kind of like a little mini course, versus having just some reference material that's curated and tame, as I say, versus I've got this here problem and I can articulate it to Google and now Chat GPT. Now with Google, I see people, I use it all the time too, just like you all do, just like we all do. I am very good and skilled at articulating the exact phrase that I need help with Google. But I observe that comes from experience, and it's not always easy for everybody to articulate exactly what they want or need. Indeed, they may not even know exactly what they want or need. And furthermore, if you are very experienced, you may easily be able to discern what's a high quality resource from what is a lower, less helpful, or even irrelevant quality resource. So the challenges with the boot camp are that we all have to use the internet, but it's not a perfect solution, but it's easier to do than grappling with the format of the boot camp. ChatGPT will probably change this. If we have time today, we can explore that. but that can probably abate some of the problems with just using the internet to learn this stuff. Now, I have this thing. I've mentioned this concept a few times over the years in here, but I'll refer to it as the statistician's dilemma. Statistician's dilemma is a very, very challenging thing. I feel it. It's my way of describing it as the statistician's dilemma. Here's the dilemma in my own words. Um, there, there is, in a sense, something I want to show any student on day one. They come, they have a problem, or they may have a problem in the future. I want to be able to show them the full speed solution to their problem. I want to show them a beautiful graph, a beautiful statistical analysis, and I want it to be easy for them to create it and interpret it. I want to show it to them immediately. I want to give them immediate gratification for the evidence that they create from their data. But what we actually show students, because there's a large foundation of concepts that underlie the creation of a beautiful, perfect analysis, we often start with the building blocks at the bottom, down here at the foundation, rather than at the top. So if the beautiful solution is at the pinnacle, we often start with these little building blocks right down here at the base. So we might tell them about how to calculate the standard deviation. We might show them about frequency data, and we might give them contrived problems that are quite simple to visualize and think about, but are completely irrelevant, silly, even completely contrived and false. May not even be easy for us to come up with relevant ones for a particular field because, for example, even in this group of people watching today, all of you have different subject interests, and so coming up with one example that suits everybody is not possible. It is often the case. The statistician's dilemma that I so named comes from something I have mentioned in here called the mathematician's dilemma. And it is articulated with a metaphor. The metaphor being that what if we weren't mathematicians? What if we were artists? And we wanted to teach our students to become great appreciators and creators of art. We might go to the museum and might go to the Tate, or we might go to the Louvre, and we might show them the greatest works of all time and enjoy them, laugh about them, argue about them, to say, call out the ones, what we don't like about certain ones. We might celebrate it. But instead, maybe we would take 10 years and start on the first few years and talk about the physics of how light reflects from surfaces and the theory of color and how to create a wooden frame to stretch your canvases on and so on. Much start down at the base. So that's the statistician's dilemma that we have when we're taking on new skills. I have this slide that I wanted to say something about. I mentioned that I created the tutorial on purpose as a tutorial format. There are different ways that people prefer to learn. There's a theory in teaching and learning about learning modalities. I know some of you may have seen me talk about this over time. I'm interested in this. We're often constrained to package the material at university in traditional classes or courses, or here at Harper they call them modules, but whatever you call them, it's totally arbitrary what they're called. It just means an expert or somebody who knows a lot about something pontificating at the front of the class to students who are passively sitting in the class. And there are all little tricks we can pack into this kind of format. And there are jargon terms for all the little tricks, but essentially that's what I mean by traditional model module. There are online courses these days. Some are very good and some are not very good. The best of the ones are on platforms like the famous Coursera. It's the their key phrase is the best quality education in the world for absolutely free. You can audit any course on Coursera for free, and it is from the best universities and lectures in the world. edX is a companion platform. It's unrelated to Coursera, but it is also the same exact spirit, high quality materials. Now, these are online courses. Almost all of them are modeled after the traditional module. Of course, we all know about YouTube and how I was just chatting with someone who's here in the chat today who will recall our conversation earlier that sometimes it's just more convenient to watch a YouTube video. Hey, it is for me too. I love to watch them. I watch them all the time. You can get some really high quality stuff. It's actually, though, if you're looking for um, a topic X, it's quite difficult because there are so many YouTube videos and it's just increasing all the time. Of course, textbooks often accompany the traditional modules. I'm not necessarily condoning this particular one. It's just that that's another format of learning that some people prefer. Web-based materials like my tutorials are very popular, and you're really spoiled for choice. There are literally millions of tutorials out there on all topics. It's hard to find a good one that fits what you want to do to the right length, that is complete on the topics you want to study, and is in a style with examples that fit you, but you're really spoiled for choice. Most of us in sciences learn on the job, so to speak, with a combination, pulling in a lot of these different sources, and we learn when we have our own data to, as an example, something we care about the answer about, and we fill in the gaps as best we can as we go along. I wanted to say a little bit of a thing, and this the eve of starting a few sessions on Python, that you don't have to choose between R or Python. You can use both. We do use both. I use both. I use R. I think there was a time when I used to say something like I use R every day and I use Python about once a month. But I'm at the stage myself where I'm using R and Python both almost every day to do different things. They're better at different things. I've been working with R quite longer than I have Python, but I have worked with other programming languages, even though I'm self-taught as a programmer. But I have published papers with programs I've written in the languages Fortran, C, C++, SAS, R, and Python. So I've self-taught a lot through my career. R is by far the best at statistics. It's by far the best at graphing data for scientists and other interesting people. It's by far the best at general scientific use and creation of evidence for scientists. It's got a great community for data analysis, by far the best community for data analysis. Python has a bigger community, but it is much more diluted. So people who are interested in Python do everything from creating apps for your phone to web-based apps to data science and computer vision. So the community on R is very focused on statistics. R is literally invented for beginners, and I think it is best for applied scientists to start with. But Python does have some advantages. It's by far the best at at least compared to R. It's much better at general computing tasks. It's made as a general computing language. It's like R is best for statistics. You'd be really crazy to use R for any modern AI application. Other than just tiddling around and learning, Python is definitely the best at AI, and it's better than any other language as well, because the tools are being created in Python. Computer vision, hands down Python compared to any other language. Automating tasks, R is not very good at it, but can do it. But Python, it's just so easy. It's a traditional computing language. Automating everything from file handling to doing services on web pages, even an academic web page. And then finally, big data, it's much better. Now, we're going to start using Python. We're going to start fast. And any of you who want to code along with me will take enough time. I've just got a simple demonstration right in the very beginning of this, even if you've never used it before, that you'll be able to read in data from an Excel spreadsheet, create an appropriate and well-labeled scatter plot with a regression line fitted to it, and calculate the regression statistics. Now, this is a data analysis example, but it's a fast one. And then I have a small tutorial that I've laid out. And then finally, I have a list that's, I think, pretty big, and it's curated by myself for resources I'm aware of and that I've actually tried both. So it's a curated list that I have vetted for quality. It's a long list, so I don't know how easy it will be for people to take advantage of it, but I like lists. So I've made a list of extra resources after today. Having said that, your first challenge for using any software system is to install the tools you need to be able to use it. Remember, I said R was easier at that. You really only need to install one thing, R itself. Most people would install R and R Studio, and that makes it so easy to start using R right away. Python, I won't say that it's hard, but there's a little more to it. So you have basically three options. If you're going to install in your local computer, these are your two options. You can install Python alone, and you'll need to install some kind of code editor. I say you need to. You don't really need to, not technically, because you could just make a text document with Notepad or your text editor of choice. But you'd be silly not to use a visual code editor. One comes with Python called idle. So really, if you wanted the bare bones of installation, there's no reason to do the bare bones of installation. I don't think this is the best way to start. But you could just install Python. It comes with its own editor called idle. I think I'd recommend almost anybody who wanted to just install Python to also, instead of using idle, to use Visual Studio Code. It's a Microsoft product. It's currently my favorite, and I've used code editors my whole career, remember. It's the best one I've ever used. It's so easy to use it, and yet it is so powerful. It's free. It doesn't have the overarching heavy-handed Microsoft stuff that some of their products have. It's just very easy to use. I highly recommend it. Having said that, I would not recommend this route for anybody who's beginning with a programming language. It's probably the hardest of these three routes to just install Python. Sounds like it would be easy, but there's more to it than that, which I won't go into. What most people would do if you must install, now I want to remove that because I've crossed through the name of the tool. You want to install Anaconda. If you must install Python yourself on your local computer, the best way to do it, the easiest way, is to install Anaconda. It installs Python for you, and it keeps track of versions. You don't have to worry about versions when you're beginning, but trust me, that's a good thing that you don't have to worry about. And it also installs, by default, two of the most popular editors, or text editors. Now, it doesn't install Visual Studio Code. I told you that's my favorite, and I think it's the best. And yet, uh, even if you do use Visual Studio Code, you're going to want to use a framework called Jupyter Lab. This allows you to mix web page-like formatted information with code that actually runs. And it's really revolutionized the way that people are coding with Python and other languages too, including R. But it has really swept like fire through through Python teaching and learning, and for beginners, it makes it so easy to come in. It also comes with another editor that I'll just name called Spider. It doesn't have the word, but it looks like this. And I like Spider a lot. I used to use Spider quite a lot. And now I didn't take immediately to these Jupyter notebooks, Jupyter Lab notebooks, but I have now. Now, if you must install on your local computer, this is the way to go. And I would probably recommend starting with Jupyter Lab. Now, the way we're going to do today is the easiest way, where you install nothing and you use a tool called Google Colab. What this is it's a web-based, it's a cloud-based entity that Google has made. They've released it to the world. It's free to use. There are some limitations, but they're not really important. They won't impact us. They won't impact you for a long time in your usage of it. You can do all sorts of very advanced analyses on the free platform that Google gives to us. It includes a installation of Python and some other useful tools already in the toolbox, and it also employs these Jupyter Lab notebooks. Okay, you can also run other kinds of files, but that's all you need to know for now. Here's what we're going to do today. And, we're going to look at, it's going to be so fast and easy, I hope, to get people going, but I'll make sure everybody who wants to gets this up first. We're going to get the interactive page up. We're going to all successfully run a data-driven example of using Python. Now, there are some exercises. They're next in there. This is a little bit out of order, but I've given an introduction to how the Python language works on this page that I have for you today. And I want to make at least 5 minutes at the end to go over a list of resources and links to different kinds of modes that I mentioned on that modes page. And I want to integrate some of those into the new Python bootcamp. So I want to make that available to you. So what we're going to do is I'm going to minimize this. And I'm going to invite you with me to click on the link for the Colab notebook. What should happen, I'll just do it. You can watch me first, and then I'll give everybody plenty of time to do it. What should happen is, now your page may not look like mine because I have dark mode on. Let me put on the light theme. So yours should look like this, unless you have the dark theme on. Over on the side, if I close this, then you might have a pane like this. There are 4 little buttons. If you push the top button, you can see a clickable table of contents on the side. I'm just going to give everybody a minute to just open that up. And then we'll keep going. Anybody has questions or is having trouble, let's just pause. We have plenty of time. We can help everybody just do this. The thing that I think you will need, if you don't already have it, is you will need to log in. You will need a Google account. You'll need to sign into Google. Yeah. So let me know when you're done or if you're having any problems. If there is anyone who does not have a Google account, think different people think different ways about this. Yeah, sure, Ben, I can. Let me spit this part out and then make sure people are going, and then I'll go back to the optimal local installation. If you don't have a Google account, in short, stop the fifth F and just make a Google account. It gives you access to lots of free, good tools. You don't have to use the Google account for social media or their email, although they give you free storage space in the cloud and free email if you want to use it. I don't necessarily use my own Google account for email, but I do use the free storage, and I do use Colab a lot, and some other things. So it's free. to do. A reason not to rely only on your work email is one day, heaven forbid, you may not be a student or employee of Harper Adams, and then all of your email will be gone. So while people are getting that up, let me know if you're successful or if you're having any problems and we need some help. But I'm going to go back to this slide, talk about the optimal installation. Just to reiterate what I said, um, these two solutions here are routes that you would take if you were installing locally, 1 and 2. Route 1 is where you just download Python and install it on your computer. This works for Macs, PCs, and Linux. And you'll need a text editor of some kind. You'll want to use one that highlights code. Idle is the default one that will install automatically. One that I would recommend, I mean, there are loads of them, and some people are very, particular about it. If you're particular, use the one you like. I like Visual Studio Code. It's not the easiest one to start using, but it's not hard to start using, and it's by far the best one that I've ever used, and it's free. I don't think this is the best way for most people, though, to use Python on their local computer. I think the better way to use Python is to install a software package called Anaconda. This is a bigger download than just Python, a little bit bigger, but it creates an environment that keeps track of all of the tools you download. I often think that R itself would benefit from using Anaconda. And back in the days when you can, in fact, use R for Anaconda. Back in the days when I used to do statistical consulting for the pharmaceutical industry, it was important for me to curate reproducible analyses for contractual reasons for particular analyses. And so I had to keep the set of R versions and the versions of packages all together. And if there was something like Anaconda for R, and there are other tools, but they're not as easy as Anaconda, it would have been so easy. So you create different sandboxes with your sets of tools, but you don't have to think about any of that. Just download Anaconda and install it, and it'll do all of the heavy lifting for you. This is the best way if you want to install it locally. And then if you don't want to install anything, there's a little bit of a trade-off with Colab, is that if you upload your data set today, which we're about to do, you upload it today, Colab doesn't keep your data set in the cloud environment. It'll forget your data set. You'll have to re-upload it later. There are ways around that. Like you could use your Google Drive to read in your data set, or you could use GitHub to read in your data set. We're not going to go over that today. It's a little more advanced, but it's so easy just to upload a single data set or even a folder with lots of data sets. It's so easy to do in Colab that it's not really a problem. That's just a recap of the different ways to access it. Okay, I assume that people who want to do this are with me now. Is there any problem? Does anybody need a minute or need some help to get Colab open? We're all okay? Okay, here's a slightly harder step, but it's less prone to needing an account or anything. Is if we go back to our schedule here, and I'll just put for convenience, I'll just put this back in the chat for people who need it. There's the data, and we need the data. So the way that I would do this is I would just, if you just want to download it to your downloads folder, I'm fine with that. My way of doing it would be to right click in Windows and save it to a place that I want to save it to. You can just download it though, and then find it on your local computer. I'm just going to pull mine over here, and you should have a data set called tuber underscore 50.excel. Just download it wherever you want. Could stay in your downloads folder if that's the way you like to roll. I'm just going to open it real quick and show it to you. This is a real data set. It's got 3 tabs down here at the bottom. I'm just going to make it a little bit bigger so we can all see it better. One tab is called data. One tab is called data full. It's got the same columns as data, but some extra columns. And one tab is called the data dictionary. This is in tidy data format, like it should be. This happens to be some data on potatoes. It's a shockingly exciting subject, I know. But we've been collecting data samples. These are destructive samples. The sample length is each of these is a sample. The sample number is represented by a numeric variable in the sample underscore NO. There are 10 samples. These are destructive samples in a potato field in a 1 hectare area on a roughly a 30-meter grid. There's a plant number. The plant number is numbered within plant samples, but it's 50 potato plants, 5 within each sample. We've counted the stems above ground for each plant. We've counted the total number of tubers and the total weight of all of those tubers. These are salad potatoes, so they tend to have a large number of tubers. This is really extreme. Some of these potatoes will be very small. Give you an idea of this, baked potatoes would tend to have about 2 kilograms. These are the total weight in grams. This one, for example, has 41 potatoes that weigh 1 kilogram or so, 1,059 grams. A regular baked potato plant will have an average of about 6 to 10 potatoes, and the potatoes would weigh about 2 kilograms. Okay, so it gives you an idea that there's more potatoes and they're all a lot smaller. That's what's in the data set. Now, once you know where that's at, here's the hard part. It's the only hard part. It's not that hard. We go back to Colab. I highlighted these. I'm just going to make this a bit bigger in case we can all see it. I highlighted these little buttons over here. One of them is the folder. If you click on the folder, what will happen is it said connecting to a runtime, and see this connecting, initializing. When you click on your space over here, it says, oh, right, this person just opened up the script, the IPython notebook. But when you click on the file, the cloud environment for Python is saying, oh, right, this person is actually serious and actually wants to use some computing resources. Let me allocate a computer resource, a unit of computing resource for them. And it initializes and starts it up. And if you click over here, you can see how much system RAM and how much disk space you're allocated. Yours may not look exactly the same as mine. Now, plain old Google Colab has some limits on how much system RAM and disk space you're allocated. And I have a Google Pro account. I pay a little bit because I use it every day myself. And they have a Pro Plus plan if you really are greedy for resources. But to be honest, the free resource is just fine. You'll have plenty for anything that we might do for a long time. Okay, so what you see when you click on this folder is you see a space that has got some example data in it. It's got some housing data. It's got something called mnist underscore test. It's got mnist underscore train underscore small, and it's got something that's a .json. That's a Java data file. So it's got some stuff in a folder, but we're going to ignore that. That's just for an example to play around with. We're actually just going to grab our tuber_50 Excel file and drag it straight over. It is a big warning that a hacker may have provided you with this file. And if you don't trust the source of the file, actually that was saying that it's going to forget your data. That's not the hacker warning. We'll get that one in a second. So what it just warned us was that when we log out of this session, it will forget the data and we would have to upload the data again. And any changes we make in the data or in the script will not be saved unless you choose to save them. Yeah, we'll demonstrate that as well before we finish. So you're golden now. If you can see the tuber XLSX file in this space with the folder icon. Just give everybody a minute or two to catch up. Anybody need any help, or are we ready to keep going? Maybe just say where you're at in the chat if you want to keep going. But get an affirmative and no complaints, I'll just keep going. I'll just wait 30 seconds. We okay? Okay. Right, so I like to see the stuff that's in my memory, so I tend to keep this open when I'm coding this stuff. The way that these pages, I haven't embedded any graphics in this, but it's a web page basically, and you write it in that language called Markdown. It's really easy to write. If you see this and you click in it, if I double click it, it shows me the code on one side and it shows me how the code renders on the other side. And the elements of Markdown that I've applied to this are that the hash mark indicates the headings or a title. One hash mark is a title, 2 hash marks is a level 1 header, 3 hash marks is a level 2 header, and so forth. Everything else here is just plain text. There are some visual elements. If I want to make something bold, what it's going to do is I can click this button and it will insert the Markdown code for making something bold. It's 2 asterisks on either side. This combo down here is a little game that Google gives you. It gamifies constant typing. If you can keep the flow going, you can get your combos up pretty high. Practice your typing. So this is just a web page that is rendered like HTML, and it just does it automatically. To re-render the cell, the hotkey is Shift Enter. So I'm just going to hit Shift and Enter, and now it just renders again. See how the cells are embossed. If I click up here, it embosses the one that's selected. Okay, so I'm just going to go away from the files, and I'm going to click up here on the little table of contents symbol. And you can see that I have this set out in some symbols. You can read this stuff on your own time, but the objective here is to just demonstrate a legitimate data task to illustrate the basics of Colab and Python. This whole script does this. It's going to take maybe 30, 40 minutes for someone to go through it, maybe an hour if you want to follow the Wikipedia links that explain some of the things. There's some simple quiz questions. They're optional. I'd recommend, rather than spending a lot of time with the quiz questions, if you don't want to figure out the answer, at least use ChatGPT. If we have time, I'll demonstrate how I would recommend doing this and make it a little bit of a game with yourself to solve the quiz questions. By the time the bootcamp launches, I will embed a web app. Already got a working version, although I haven't released it into the wild yet, that allows students to use an interface that I control, that I've trained to act as a very kindly statistical consultant for students who want to do data analysis. This isn't a teaching tool, something I want to use with people like you here, something I'm interested in. So, but you can use it on your own. Mine, I hope, will work really well, but maybe I'll demonstrate that. I will demonstrate it in here in the future. And then I want to go through that resource file that I showed you. But first, let's look at this simple example. So I'm here on 1. You can navigate through this with this clickable table of contents. Basically, the code that we're about to run, it reads in a small data set on potato size. Look, I've even found a typo here. You can just fix the typo and bam. Following code is to read in a small data set looking at potato size, and we'll print the first few lines of data. It's going to create a graph looking at the relationship between the number of potatoes and the weight of potatoes for a single potato plant. It's going to print the results of linear regression for these variables. All you have to do is click on the play button to execute it. You don't need to worry about understanding the code. So I'm going to make this small enough that we can just kind of look at all the code. This is the entire code. This is the play button to execute it. Let's just click that and see what happens. Here's the hacker warning. If you don't fully trust the person that is giving you code to run, you must not run it. It's just that simple. So I'm going to run it anyway, because this guy's fairly trustworthy. So we should get some output that looks like this. If any of you scrolled down, you would have seen there was already some output in there, and it saves the output in the folder. So I had already obviously run this when I wrote it. It just saved the output in there. But I just wanted to look at what we did. We've read in the data. We just look at the output. We've read in the data. We've printed out the top 5 lines of the data, the header. We've created a graph that is a scatter plot with a regression line and then labels the axes appropriately and all that junk. And I've printed out the results of the regression, including the slope, which in this case is 23. It's the rise over the run. It's the total weight of potatoes against the total count of tubers. So we do expect a positive linear relationship, and that's exactly what we see. We've got the intercept, 287, 287 grams of potato weight. Remember, that's the intercept when the number of potatoes equals 0. Okay, does that make sense? It doesn't actually make sense. This regression, that's why extrapolation on regression is a bad idea. We shouldn't really extrapolate below about 9 or 8 potatoes. The R value is 0.71, 0.718. So R squared is, around 0.5 or so. E value for this is in scientific notation. It looks even worse than the default in R. Very small number indeed. This is a highly significant statistical relationship. And the standard error for the slope estimate is 3.237. My point with doing this is just to show that a small amount of code to read in the stuff, we can just look back in at what we've done. I'm going to make it a little bit bigger. Only a small amount of code is needed to run the entire analysis. I've opened the toolboxes that Google has already installed for us. There's one that makes plots. It's called Matplotlib. We've imported that, and we just call it, because it's a shorter word, plot. Notice when I mouse over this that I get tooltips. This is a big advantage of Colab. Colab's pop-up tooltips, they work really well. They're in there for all the packages that are installed. They're just as good, and dare I say, I actually hate to say this, but they're a little bit better than the ones that are embedded in RStudio. Pandas is another one. We use this for reading and data structures. And the SciPy is a statistics package. It's the reason that I started using Python for the first time a long time ago was SciPy, and we're importing the linear regression function, linregress. Okay, so we read in our data set, The way these functions go, again, don't worry about remembering any of this. Is just by way of an example to show you what's possible. We're calling the pandas data object, PD as PD. PD.read Excel is equivalent to the R code where we name the package : the name of the function. So this just calls the pandas function read Excel. We read in our Excel, we're reading in the data sheet called data, printing the head, that prints the header, pulled out of the data object, the total count, the total weight. Look what happens if we mouse over this. Gives us a nice little, this is also pandas at work because it's a pandas data object. It gives us some descriptive statistics without writing any code. It's also something, I really hate to say it, it's a little bit nicer than R in RStudio. Performing the linear regression, though, is not nearly as nice as R and RStudio. It's a million miles away. If you were going to use, if I were going to use for regular statistics, Python, I would write my own package that had a sensible output and formatting for statistical analysis. For the histogram, all you have to do is select the name of your variable and mouse over it, and just don't touch your mouse. It's a really neat little thing that Colab started doing about a year ago. It's amazing. You can mouse over anything, and it will work. What we do next is we create the scatter plot, and we draw the line fit on it, and then these lines label the different axes, and then these lines print out the stats. Now, that hour went really fast. I have to go to another meeting, but I just want to point out that I'd recommend having a look at the Python resources. It's a Word document. Finish the Colab tutorial by all means, but you can look at my document. I want to point out a couple of the things on it. One is that I've got this divided into courses and problems and projects for your own learn while you do a project, some books that I fancy that I've used, some miscellaneous ones. Okay. One that I want to really point out is if you're serious about it and you have lots of time to devote to a course, you want to take Harvard CS50. This is widely viewed as the best introduction to Python programming in the world. It's been refined intensively by some of the best teachers of beginning programming, and it's made for non-programmers. So if you want a full course, another one that people really like and I love is Dr. Chuck's. It's Chuck Severance, Charles Severance's code. He wrote a book. The book is linked down below, and he's got a whole course with great videos. He's a University of Michigan professor. His course is so popular that it's available on Coursera, edX, and on Free Code Camp, and they all have the videos, the free book, everything. Everything's linked here. Unfortunately, I have to go to this meeting now, so I'm going to stop the video. I don't have time for questions, so if you do have questions, post them